So today we're going to be working with Taylor and Maclaurin series. So for starters, we should probably know what a Taylor series is. So yesterday we learned that we can rewrite most functions in the form of 1 minus 1 over x. That way we can relate that to the following partial sum, right? But not all functions are easily able to be going into this form. So in times like that, what we can use instead is a Taylor or a Maclaurin series. Maclaurin series is just a specific version of a Taylor series, as we will see later on. So if it's not easily able to be given, you know that the sum from n equals 0 to infinity if f of x equals this, then this value right here equals c0 times c1 times x minus a to the first plus c2 times x minus a squared plus c3 times x minus a cubed, and then so on, right? And then it might look daunting at the time, like how are you supposed to be finding all these c values, right? But if you just plug in a into f of x, so f of a equals c0, right? Because then all these values would approach 0. And then f prime of a equals, here let's take f prime of x. So f prime of x equals 0 plus c1 plus 2c2 times x minus a plus 3c3 times x minus a squared dot dot dot, right? So now f prime of a equals c1, then f double prime of a equals f double prime of x equals 0 plus 0 plus 2 c2 plus 6 c3 times x minus a dot dot dot, right? So f double prime of a equals 2c2, f triple prime of a equals 6c3, and then so on, right? So we can see that any function, right, that any function for which its derivatives exist, that is very important. You can write f, this is very important. So let me erase this very quickly. That's a bit better. You can write f, okay, no, now it's a bit too wet. You can write f of x equals the sum from n equals 0 to infinity. So you know that f of a equals c of 0, right? So to get all of these, right, we're taking f to the nth term derivative of a over n factorial, right? Because to find c3, right, we would take the third derivative and then you would divide it by 6 to actually isolate for c3, because that's how math works. And then times x minus a to the nth. So this is actually a very important formula. After I erase all of this, we will see how we can apply it. And not so much as how we can apply it, but we're going to be looking at 3 maclurin series that are very important. And then I'm going to be going over the first problem from Mrs. K's notes today and how she solved it. So the maclurin series, here, let me write it here. A maclurin series is just the Taylor series where a equals 0, right? And that's all what's special about it. So now let us move on to our first problem. So I'm going to be moving that up there. And yeah, let's work on some Taylor series problems. So the following Taylor series are some of the ones that like show up a bit more than the other ones, and you should know like how to manipulate them, what the values are, and all of that. So the first one that we're going to be trying to find is the maclurin series for e to the x around x equals 0. So the first thing that we should always write is what is the definition of the Taylor series or maclurin series. So in this case, it's the sum from n equals 0 to infinity of f to the nth power of a over n factorial times x minus a to the nth. So our a value in this case is 0, right? So now let's start off. F of x equals e to the x. F of 0 equals 1. F prime of x equals e to the x. F prime of 0 equals 1. I feel like it's redundant for me to just keep writing this out. So as you can see, f to the nth of a, in which case is 0, is always going to be 1, right? So now we're like basically done. So f to the n of a equals 1. So this right here is equal to 1. The sum from n equals 0 to infinity of 1 over n factorial times x minus a, which is equal to 0, so x minus 0 to the n, which equals x over n factorial. The sum from n equals 0 to infinity of x over n factorial. And now, so as you can see, this can give you your radius, some conversion, all of that, because, well, it's all real numbers because of whatever. So this is the maclurin series for e to the x. You should keep this memorized. And now let's move on to our second example. I don't really need to delete that. Erase that around x equals 0, but I guess I did, so can't really do anything about it now. And now let's move on to cos of x around x equals 0 again. So as always, my advice is the same. We first write down what the definition of a Taylor series is. So as you can see here, this is our definition, and now we can start. So first we got f of 0 equals, no, f of x equals cos x, f prime of x equals negative sine x, f double prime of x equals negative cos x, f triple prime of x equals cos x. So then, no, this is incorrect. Equals x, and then so on, and you know that this repeats after 4 times because that's just how the function works. So now let's plug it in. F of 0 equals 1, f prime of 0 equals 0, f double prime of 0 equals negative 1, f triple prime of 0 equals 0. So as you can see, when it's equal to 0 and 2, when n equals 0 and 2, you have a value. But these zeros, we can just eliminate altogether from the equation, right? So now we need to be able to relate this right here back to this. So f to the nth derivative of a of 0 equals negative 1 to the nth power, right? Because when f equals, so now if we rewrite this to equal 0 and then this to equal 1 and then that value to equal 2, and we just get rid of these, then the only thing that's remaining is negative 1 to the nth power, right? But we've got to remember that we removed all these, right? So there's, the values are like 0, 2, 4, 6, 8 of like the actual n. So let's rewrite this in. So now our actual series will be, here, let me write it right here. The sum from n equals 0 to infinity of negative 1 to the n, because again, that's our f to the n, f derivative of n of a times 2n factorial, right? Because when you plug in 1 here, you actually need 2 over here, times x minus 0 to the 2n, right? Because once again, when it's 1 here, you need 2. So let's simplify this. And this is our maclurin series for cos x. You might want to write this down. I don't know, but you should keep this memorized. And now let us move on to our next problem at hand, which will be, you can wait. F of x equals sine x. Now this one's going to be very similar to the previous one, so you can try doing it yourself, but I'll work you through this as well. The first step is always writing down what the definition of a Taylor series is. So now let's start with our process. and then once again it will repeat, right? And since it's around x equals 0, let's start plugging in. So at this point, if you want, you can pause and try to find the relation, but let's continue with what I'm about to be saying, and I'll work you through the remainder. So as you see, we can do the same thing here, but now you see that the first thing actually equals 0, and the third one equals the second. And the second equals the third, right? Wait, what am I saying? Wait, no, I have my numbers mixed up, that's why. And the third number equals the second actual. What am I saying? Okay, regardless, once we cancel these out, right, you can see that we're once again taking it in pairs of 2. So you want this one, then this one, right? So you see that you'll need 2n, but we're going to be shifting it up 1, right? Because when you plug in n equals 0, you want the first number here, right? So now you're going to be getting 2n plus 1 factorial. And now, once again, so in this case, when you plug in 1 as n, you want it to be positive, and then you want it to be negative at 2. Wait, no. So when you plug in 0, you want it to be positive and then negative at 1, right? So in this case, you'll plug it in as 0, and then you'll plug it in as 1. So now you can see it would be 2n plus 1. So in this case, it would be negative 1 to the nth times x minus 0 to the n. This isn't to the n. This is again 2n plus 1 because you want it to be matching this value over here. If you don't understand why it's 2n plus 1, it's because we're removing every other thing. So essentially we're not incrementing it by 1, but rather we're incrementing it by 2. And then you need a plus 1 because at 0 you're going to be getting a 0, so you want it to start at 1. So I guess that, like, if you really want to, you could change this n equals 0 to a 1, but that's not how we're supposed to be doing it mathematically. Just account for the shift over here. So this equals sine x, right? And now, let us move on to the first problem from Miss K's homework. Or it wasn't really homework, it was more like an assignment. And in that, she asked us to do something different. Instead of finding the series, she asked for the polynomial approximation of a value, which is actually about as easy as the actual thing. So in this case, she asked for the Taylor polynomial of root 2 centered around x equals 1. And it was using root x, I believe. Let me just check. Yes. So we know our f of x equals root x. And this is an actual application of it. And she said use 4. Yup. And then you want the 4th degree. So instead of having to find the entire thing, she's asking for a specific value here. So I'm not going to be evaluating like all the numbers because I feel like that's redundant. That's a waste of my time. You all have calculators. If not, you're watching it on something like a screen that has a calculator. So I'm just going to be showing you how to do it. So once again, we need to write it. But as you see, it says 4th degree, right? So in this case, it isn't the sum till infinity, but it's rather a finite sum of f to the n over a over n factorial times x minus a, which is equal to 1 to the nth. So as you can see, we can start. So let's first find out f prime of x. So here, we can just start immediately. So this equals f of a over 0 factorial times 0 minus 1 to the 0th. So f of a, so here, let's write out these values. So f of a equals root 1. F prime of a equals 1 over 2 root 1. F double prime of a equals, this is negative 1/2, negative 1 over 4 root a, root 1. F triple prime of a equals, this isn't, so this is x to 3/2. So 3 over 8 times 1 to the 5th rooted. And now, this is to the negative 5. And now the final one is, this is again to the negative. And then f to the 4th of a equals negative 15 over 16 times 1. Okay, so let's just get rid of all of these. Ooh. So now we can clearly evaluate everything, right? So f of a is equal to 1. Wait, yeah. Let me just write it like this, plus f prime of 1 over 1 factorial times, okay, so then this would be times 0, right, because, no, this is not. Since we're finding f of 2, we're going to be seeing where this comes in. But this is x times x minus 1 to the 1st plus f double prime of 1 over 2 factorial times x minus 1 raised to the 2nd plus f triple prime of 1 over 3 times 2 times 1 times x minus 1 cubed plus f quadruple prime of 1 over 4 times 3 times 2 times 1 times x minus 1 raised to the 4th. Right? And now let's evaluate for x equals 2, because that is what we're trying to find, right? So we have all of our values here, and now we just need to plug in. So I'm going to do it down here. So now you get f of 2 equals f of 1, root 1, 1, over 0 factorial 1 times 2 minus 1 to the 0th. Okay, so 2 minus 1 is equal to 1. I don't think that anybody needs me to do that much plugging in. So times 1. So yeah, I'll keep the times 1 there. Plus f prime of 1, 1 over 2 times 1 divided by 1 factorial is equal to 1. Plus f double prime of 1, we can come up here. This is equal to negative 1 over 4 times 1/2, because that's what 2 factorial is equal to, times 1, right? Plus f triple prime, we found that, that's right here. So that's 3 over 8 times 1 over 6 times 1 minus 15 over 16, 15 over 16 times 1 over, what is that? That's 24 times 1. Right, you don't need me to raise 1 to like all those powers. You know what it's equal to. So now we can evaluate here. So it's 1 plus 1/2 minus 1 over 8. You see, you can multiply that 4 by that 2, 8, plus 3 over 48 minus, it's, is this 144? No, 48, so plus 5 over, minus 5 over 128, right, which equals a number, and apparently it equals 1.398, about this number. So as you can see, this is pretty easy. This is called Taylor polynomial, where you're summing it not to infinity, but actually a certain degree. I'm not like entirely sure what the actual Taylor series for root x is. It's a pretty complicated thing. It's like, it can be written in computer science. That's all I know. And the degree is actually the sum that you're going to. So yes, that is the lesson on Taylor and Maclaurin series. Good luck.